Hello and welcome. Today we'll be looking at elongation in case of a taper rod. And the above diagram is the diagram of a taper rod that is subjected to a uniform load P, and the outer diameter, that is the top diameter from this point to this point, is D1, and the bottom diameter is from this point to this point is D2, and the length of the taper rod is what? Is L. Now, for us to calculate the elongation, we know that from elongation formula, we know that the L is equals to PL all over AE. We know this already. Now, we would have applied this formula to find our deformation here. This is the elongation. But we observe that as we move from this point to this point, the area keep increasing. That is, we move from this point to this point, we move from this point to this point, the area varies. So we don't have a uniform area. So every other things here remain the same. So how are we going to do this? So it means this formula here, we cannot apply directly to this. So we must do some things. Now, for us to be able to get the elongation of this taper rod, we are going to consider a differential element, that is a small part, which I always refer to as a strip, but which is also known as a differential element. That is, you can section the taper rod any part you like, but section this part. All right, and from this point to this point is the diameter of the differential element, and the height, that is the length of the differential element, is the S, and the distance from this point to this point is S. So let's go into this. All right, so we are going to consider just this differential element. When we get the deformation now, we integrate it. When we integrate from this point to this point, then we get the total elongation of this taper rod. All right, let's get started. All right, considering differential element. Considering the differential element. All right. We know that the deformation formula is equals to PL all over AE. All right. All right. But what is the length of this differential element? It is what? DS. So it shows that this formula is going to change to PDS all over what? All over AE. All right. So now, how do we get the area of this differential element? We are going to calculate the diameter first. Once we get the diameter, then we can get the area. So the diameter of this differential element here is this. But how do we get the diameter here? So we are going to use unity method to get the diameter. So from unity method, we know that the diameter D will be equals to D1 minus D1 minus D2 all over L multiplied by what? By X. This D1 minus D2 all over L, then multiply by X. All right. So now, this is what our diameter is going to give to us. Now, we cannot therefore replace what we have there with any constant value. Let's say K. So let K be equals to D1 minus D2 all over L. Therefore, it means that D now will be equals to D1 minus KS. All right. Now, let's find our area now. Area is equals to what? Pi D square all over what? 4. So it means area here will be equals to pi into D1 minus KS all square all over what? 4. All right. So now we can now therefore substitute this in our deformation formula. So it means the deformation of the differential element will be equals to P ds all over what? All over A. Our A is pi into d1 minus ks all square all over 4, then what? Then e. So this formula here is the deformation of what? That is the elongation of the differential elements. All right. So now the next thing we are going to do is for us to get the total elongation now. For total elongation. For total elongation. For total elongation, we are going to integrate. So we are going to say the L will be equals to now we know what is here. We can rewrite it as this as 4p. This 4 will move up and be left with pi e. So it's going to be all over pi e into what? Into d1 minus ks all square. Don't forget we have the AC. All right. So we are going to integrate what we have here for us to get the total elongation. So we are going to integrate. So for us to do we are going to integrate from 0 to what? To L. That is from this point 0 to L. Don't forget the total length is L. And we are moving from the bottom to the top. So that is the lower from the lower limit to the what? Upper limit. So from 0 to L, then we have 4p ds all over what? All over pi e into d1 minus ks all square. All right. Now the next thing is we are integrating respect to s. So 4p pi e, everything becomes a constant. They'll come to the back of the integration sign. So this is going to be 4p all over what? Pi e. Then we are integrating from 0 to L of what? Of the s. All over what? All over d1 minus ks all square. All right. So how do we integrate this? Let me quickly show us. So now we are going to say let u be equals to what? D1 minus ks. So we are going to differentiate u in respect to s. So the u all over the s will be equals to what? Going to be equals to minus k. So we are going to make the s the subject. The s will be equals to the s will be equals to the u, that is minus 1 all over k u. All right. So now we can therefore go back there. We're going to have, we go back there, we are going to have L to be equals to 4p all over what? Pi e, integration from 0 to what? To L. Then we are going to be having the s. Sorry. We're going to have the s all over what? All over u squared, because we already said u will be equals to. All right, but don't forget our the s is equals to what? Minus 1k. So that this we can say the L will be equals to 4p all over pi e, then integration from 0 to L of 1 all over u squared multiplied by the s. What is our ds? The s is minus 1 all over k u. All right. So now we are now integrating this from we are now integrating u in respect to the u. So it means 1 all over k becomes a constant as well. We'll bring it to the back, and we are going to have the L to be equals to minus 4p all over what? All over pi e, then k here. Then we are integrating 0 to L of what? And you know we can write what we have here in form of u to the power of minus 2 u. All right. So by the time we integrate this, I'm going to have the L to be equal to minus 4p all over pi ek. So it's going to be u to the power of minus 2 plus 1 over minus 2 plus 1. So we are going to have u to the power of minus 1 all over minus 1. And we are moving from the 0 to what? To n. So you agree with me, this minus, we cancel out this minus here. Then we are going to have everything, this bracket to be the L all over 4p all over pi e k into 1 all over u, right? But what is u? U is nothing but what? D1 minus KS. Then we integrate from 0 to what? But don't forget, we already said our K is equals to what? Is equals to D1 minus D2 all over L. So we are going to substitute this here. So by the time we substitute for our K, we are going to have our total elongation to be equals to 4P all over what? Pi E into K. Our K is D1 minus D2 all over N into 1 all over what? All over D1 minus K into K is D1 minus D2 all over L and S. So we are moving from 0 to what? To L. All right. So the next thing we are going to do is we are going to substitute for our lower and upper limits. And we are going to have our the L, this our the L be equals to going to be equals to 4P all over pi E into D1 minus D2 all over L into, so this is going to be 1 all over D1 minus, we are substituting for S, D1 minus D2 all over L, then L here, minus 1 all over D1 minus D2, D1 minus D2 all over L, then 0. Then we close the brackets. All right. You observe that this L here, we cancel out this L. Then everything here becomes 0. Because 0 multiplied by this bracket, 0, 0 divided by L, then 0. So from there, we can therefore say the L will be equals to 4P all over pi E into D1 minus D2 L all over L into, then we'll be left with what? We'll be left with 1 all over D1 minus D1 minus D2 minus 1 all over what? D1. So from here, we'll clear the bracket. Minus times D1 is minus D. Then minus times this is plus. So we are going to have this to be what? To be minus D1 plus D2. Then you observe that this will cancel out this. Then we'll be left with 4P all over what? Pi E into D1 minus D2 all over L into 1 all over D2 minus 1 all over what? D1. All right. So from here, if we find the LCM of this, let's do this somewhere here. 1 all over D2 minus 1 all over D1. The LCM is D2, D1. So D2 in D, we cancel out D2, D1 times 1, that is D1. Minus D1, we cancel out D1, leaving D2 times 1, that is D2. So we can replace 1 all over D2 minus 1 all over D1 with what we have here. So it shows that our DL will be equals to 4P all over pi E into D1 minus D2 all over what? L, then into D1 minus D2 all over what? All over D2 D1. All right. So now from here, this L will come back up. This we are going to have the L to be equals to 4DL all over what? All over pi E into D1 minus D2, then into what? Multiply by D1 minus D2 all over what? All over D1, D2. So this will go to this, right? Then our total deformation, that is elongation, will be equals to 4p all over pi e p1 p2. So this is the elongation, total elongation of this tapered rod. Leave you learn something here. Please don't forget the formula, and in case you are asked to derive this is just the process on how to derive. Please don't forget to give this video a thumbs up, and don't forget to share to your colleagues who might be in need of this. Thanks.